what we will be doing is whenever we have a new observation, we will make a reconstruction, and then we can make a new prediction. Now, what happens if you do not get any observations? Say you want to predict out in the future. Basically what you do is that you just keep running the prediction step. With no new information, you just make the prediction of the state and the covariance of the state. Then you can always look at what is the covariance of the observation equation from down here. Because this, as long as you just store the covariance of the state, well, everything else are just constant. So what you need to store are those two up there. And you should also kind of look into the question, what are you asked for? Are you asked for information about the state, or where you are predicting future observations to be? So you should kind of keep track of whether you asked for something from the system perspective, or where you're going to get measurements. Sort of like, how confident are you about where the state is, and what is the prediction interval that you have for observations? Now I'm maybe over-exaggerating sometimes. This is, of course, assuming that the future input is known. Sometimes you'll have to predict that as well, but let's just say that we know it for now. If you have to predict it, you should somehow include it into the model. Now, just a little bit of history. Why do we call it a Kalman filter? Because Rudolf E. Kalman, he made this algorithm. He was actually not the first one. Someone named Peter Sverling and Torvald Nikolai Thiele, they made something that is quite similar. A little bit before, but whatever. So when was this first, you can say, really used? That was when Kalman was visiting NASA Ames Research Center, and for the Apollo mission, well, it was a bit before our time. I don't know how many of you have seen one of the Apollo capsules. They're not that big, they look like very old-fashioned. But in there is a computer, also quite old-fashioned computer. And what they need to do whenever they're figuring out where are we right now, they have some instrument to measure that, but of course those are noisy, particularly when you're out there in space. Prior to GPS and all these things, you have a lot of different other measurements. So that was pretty much, you can say, the most famous first implementation of the Kalman filter. That is into the navigation computer of the Apollo capsules. So that's kind of one thing to remember. It did work then, it still works. And you can, well, look at Wiki if you want to look for more. So what is the foundation of this? Basically, and now I will go back to the first lecture again. If you take the linear projection theorem from slide 35 in the first lecture, defined here, the expectation of y given x is the expected value of y, and then this out here construction. The difference here relative to how we use it today is that here today we swapped x and y's, because this was the expectation of y given x. What we've done today is to say, well, we observe y, so every x here should be a y to get to today. So the linear projection theorem is basically how are x and y, the means and variance and covariances, connected. And if we call x a state, what do we need to do? We have a lot of observations, and we have to kind of use all the previous observations that we have up here. And then what we do is that we look at the conditional expectation of xt and yt, both given all the previous observations. We know that when we get through the filter, we said that it's fulfilling the Markov property, so we don't need to use all the history, but for now, let's just do that. And then from the linear projection theorem that we have right there, the expectation of x given y, as we have it there, is equal to the mu x. That's the expectation of x given all the previous y's, plus the covariance of x comma y, the covariance of x comma y given all the previous y's, and then the inverse of the variance of y given all the previous y's, and then finally y minus the prediction of y minus the prediction of y here. For the variance equation is given down here. The variance is, for this update that we do here of reconstruction as we're doing, is the variance of x given y and all the previous y's is equal to the variance of x only giving the previous y's minus, then comes the covariance basically again between x and y given all the previous y's, and then the inverse of the variance of y, we have it here, and then we have the covariance matrix of x comma y. So basically what we've written here is just the linear projection theorem from the very first lecture, where everywhere there's added a condition on all the previous y's. We did that also actually in one of the first lectures. So if we just repeat the equation from the previous slide, well, let's just take this and try to look at it not as what we looked at in the linear projection theorem, but to look at it relative to the definitions that we're using in the Kalman filter. So, if we take it step by step, expectation of x given all the previous y's, given y, that is the expectation of t, xt, given information up to time t. So the expectation x hat t given t, I could write it as minus k, where k can be 0, just to make it generic, is the expectation of x t given y t, let me make it minus 1, given y t minus 1, and all the previous y's like this, and t given t, well, that's just the same way I just write yt in there. Expectation of xt given yt and all the previous y's. So, just as a recap, and then we have the covariance between xt and yt, given all the previous. That's the covariance between x and y at time t given t minus 1. Then we have the inverse variance of yt given t minus 1, like this. And then we have the prediction error, yt minus the expectation of yt given all the previous y's. We have it here. And for the variance, we have the updated variance of xt given yt is equal to the predicted variance xt given t minus 1, as in given all the previous y's, minus the covariance of xt, yt given all the previous observations, so that's t given t minus 1. And then we take the variance again, inverse variance of yt, as up there. And then we have the covariance matrix of xt and yt given yt minus 1. So this is the equations. And now I said, well, the Kalman gain, how will we define that? That is the factor that is listed right there. The covariance between x and y times t given t minus 1 multiplied by the inverse of the covariance of y t given t minus 1. This is where, and then you have to kind of, well, there are some things that doesn't match completely when you just compare the reconstruction equation there and here. And maybe I should just spend the time filling in the blanks there. So we define the Kalman gain kt as sigma xy t given t minus 1, the Kalman gain at time t, and then the inverse of sigma y t given t minus 1. Now, the easiest, what is this equation up here? It's fairly clear what happens right there. Oh, sorry, right there. Yt minus the prediction of yt. The prediction of yt is c times this prediction of xt. That's fairly obvious given the definition of the system down here. So, oh sorry, given the observation equation down here. What is, you can say, not so obvious is, well, what is the relation between this expression here and the corresponding expression there? The easiest way is to just take this and just multiply in. So the Kalman gain, oh sorry, it's the Kalman gain times sigma yy given t given t minus 1, and then the Kalman gain transpose. If we insert the Kalman gain from up here, we get sigma xy t given t minus 1, then the inverse of sigma yy t given t minus 1 inverse. That was the Kalman gain. Now we need sigma yy t given t minus 1. And then I should post multiply by the transpose of the Kalman gain, which means that I have to transpose each of the elements and flip the order. So this is a covariance matrix, so the transpose of this is itself. So I'll just write sigma yy t given t minus 1 inverse, and not the transpose, even though it should be there. And then I should write this one here, transpose. So I'll give it a parenthesis just to be able to write it, the transpose. Sigma xy t given t minus 1 transpose. And when you look at this, here I have sigma yy on inverse on pre-multiply on sigma yy. Same time indices, so they give us just the identity matrix. So this is equal to sigma t given t minus 1 xy. And then we have the inverse, sigma inverse of sigma yy, t given t minus 1 inverse. And then we have the transpose covariance, sigma xy, t given t minus 1 transpose. And that is indeed what is written just there. Now the only thing that is not well defined is when we have this definition of the Kalman filter, how does that correspond to the definition up there? You have sigma yy, t given t minus 1 inverse. You have that here. That's good. Then we have sigma xx, t given t minus 1. But here I have sigma xy. So what is this? This is the covariance between x and y. And up there it's given as something different. So let's just look at that covariance. So the covariance of x comma y, I will remove the subscript of time because this is just a generic thing. That is the covariance between x and y. Well, that's the easy part. It's the covariance of x, and now we know that y is equal to c times x plus some noise. So we'll plug that in. C times x plus, I'll just write epsilon right now for some noise. This is a linear operator. So this is an operator, so I can look at this term with the first term and with the second term independent of one another. So it's the covariance of x comma cx plus the covariance of x comma epsilon. Now this epsilon t here is uncorrelated with everything else. So this last term here, what is that? That's a 0, exactly. So what we're left with is the first term here. We have c times something here on the second element. So what we get out here, I can take this coefficient and move it outside. When you calculate the covariance here, it's x times this transpose, which means that c comes out transpose on the right-hand side. So this is the covariance of x comma x, c transpose plus a 0, which is equal to sigma xx c transpose, which was just what we needed to go over here and write sigma xx, and I can write dot 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 there, t given t minus 1 on c transpose, and then the inverse of sigma yy, t given t minus 1 inverse. So using the linear projection theorem as a small helper, then we are now at a point where we defined whatever. 2 seconds. That should help. So now we pretty much kind of derived how to go from the linear projection theorem down to covariance matrices. And then the Kalman gain is called a gain because it determines how much the one-step prediction error influences the update of the state. So if you are into electronics of other kinds, you have a gain, which is pretty much what do you multiply with when you have a signal. And here the signal is the prediction error. So this is basically the predictions up there, which gives us the prediction errors, x t plus 1 minus x hat t plus 1 given t. There's an error that comes from the reconstruction not be the true value of x, and there's an error coming from the noise to the system. And likewise for the observation part. And that is, you can say, another motivation for why the error structure is like this when you do the prediction. And here the prediction covariance y, y is also stated and written out, and also the covariance between x, y, how to do this is also included. We won't actually need this because we did all the calculations already. So, getting back to the example with a falling body like this, let's assume that we have this positioned 10,000 units above ground. Here, we leave it 10,000 meters above ground. We say it is a standstill. We say that we know exactly where it is. And we assume that we have a uncertainty on the observation that corresponds to a standard error of 100 meters. So a variance of 10,000 meters. And for noise, well, these up here are given. Those are the ones that we kind of pre-calculated early on. Then we have some system noise, comes from, say, turbulence and other things, just postulating things. And the observation noise is this variance corresponding to a standard deviation of 100 meters. And I know that some of you in here could probably make something that is more accurate than this. But that is just to give an example. If we take this, now we have the initial values here. We know the initial position, we know the initial covariance, and we know the prediction variance out of this. And what we do is the prediction, since C is at 1, 0, our prediction is just the first state that we have in there. So what to do? I made a small simulation code with this. Basically, you can look at it in details later. I just initialize all the different matrices that we need, the initial position, and the outcomes where we're going to read things. There's one thing here that is important. As I stayed out there, I'm allocating space. So I make room for a matrix that can hold all the x's that I want to store. Likewise, I make room for n values in y. So I'm going to simulate this 300 steps forward. You will see later that I will not need that many steps, but I'll just do that. The actual simulation is to say that what I did first was initialize as time 1 or 0, and then I go from the next one through n, and I just say that my current or next position is a times the previous one. I need this drop equals false to make sure I have the right, keep the right orientation, plus b times the gravity, plus, and then I do a matrix of column of 2 random normal values, and I multiply that on a sigma matrix. I do the Cholesky factorization, I'll get back to that. And then I make an observation, which is just C times the state I've made, plus some noise. And then the last 3 lines are here just saying, well, I figure out when does X become negative. Because usually when things are dropping, they do not get too far into the ground. And then I just say, well, that's my n hit. The first negative, and I'll subtract 1 from that. That means the first n hit observations are above ground. So I skip the one where it hits. Can you figure out why I do the Cholesky factorization of sigma there? As a hint, I can say the observation here is univariate, and I just multiply by the square root of sigma 2 here, because that's a scalar. How many of you have not heard about the Cholesky factorization before? Which means that half of you should be able to answer.
Since the sigma 1 matrix is a covariance matrix, it's symmetric, right? The Cholesky factorization gives you like a factorization of that matrix into a lower and upper triangular matrix that you multiply together. So I guess if you take the Cholesky factorization, you would get in R probably one of those. That corresponds to kind of taking the square root of it, and you only get the part of the covariance matrix that you need because it's symmetric, so it doesn't need the last element.
Yes, fully agreed. Basically, the question, the challenge is we need to generate a multivariate random normal vector. But what we can do easily is to generate elements, but they're correlated. It's a bivariate system. So we need to respect the correlation structure that we have here. But we need somehow to make this into a standard error rather than to have it as a variance, because what we do typically is that we create a standard normal random variable and then we multiply with the standard error to get something that has the distribution that we want. Oops, I was on too long. So what we do is very easy to get standard normal distributions. Also multivariate, you just get 2 numbers. But if you multiply by some coefficient, you can change the covariance structure like this. And we know that when we multiply by a scalar, in this case Q on Z, then if Z has covariance matrix, the identity matrix, then the covariance matrix for Y will be Q times Q transpose. So that means that if we can create Z as some standard normal, we can do that easily. That's what we do right there. To make a column of 2 standard normal variables that are non-correlated, then if we can find a matrix Q that multiplied by itself gives us the covariance matrix that we want for the data, then we hope safe. And that is, as you said, well, the Cholesky factorization is one way to find 2 matrices where you take the matrix and multiply by the transpose. Then you get something that is a symmetric matrix. So that's the reason. It's basically just to find a way, a hack, to get something that we can multiply to scale the covariance with the covariance matrix to get the right correlation structure of the noise that we have. So what does it look like? Could look like this. I will go quite quickly through the next few slides because I want to show the same thing in R because there's one thing missing in my slides here. There. So we have the observations. it looks, at least to me, like what I would expect. You have time here, and then you have the altitude. And basically, you should expect kind of a second order polynomial falling down there. That's basically what we get with some noise. Now we're going for the Kalman filter of this. We get the first observation like this. Initially, well, the covariance matrix here, we assumed that we knew exactly where we were. So the Kalman gain will be 0 initially. That means that we will not make any updates of the system because we knew exactly where we were. So even though we get an observation, we won't do anything. And the reconstructed variance, as you have it down here, since this is 0, well, we are also staying at the same place. Now we make a prediction, A times the state that we predicted. So we move a little bit downwards with the acceleration. And that also, now we start to add, I don't have this here, but I have it for this over here. For the prediction of the state covariance matrix is A times the previous covariance, the reconstructed covariance times A transpose. Well, this was 0, so we just add the noise, for the system noise matrix here. And when we then take and add these two things together with the observation noise, we get a slightly increased noise estimate out here. Now, I will do this again. So basically, I now just step forward one step in time, do the whole thing again. I get a new observation, which is 10,046. Now, my predicted covariance matrix was no longer 0, so I get a Kalman gain. Now I calculate my Kalman gain. I make my reconstruction like this, and I calculate the covariance matrix, the reconstructed covariance matrix. It's again very close to just be the system noise. The next thing is to make a prediction, like what we have down here. And our velocity is now increasing. And we can also see that the covariance matrix now for the prediction is increasing quite a bit. And the covariance for the observation prediction is still not increased that much because the uncertainty of our measurement is still much greater than this. I will do this again. Go through the same. For each observation, I just go through each of these steps over here. That's all there is to it. If I do this, what I get out is something like this. These are just the first 10 steps. Some observations, how they are around here. The red line is the reconstructed position, and the blue is the velocity using this scale over here. So I start with no vertical velocity, and then I just have a linear increase in velocity. And of course, what I should do would be to add uncertainty on all these things. I think I've said that so many times that I should also do it myself. So I will do that. The simulation code here is exactly the same. And if you just look at x as it was before, then you will see that if I do not constrain myself, I would be moving at 2,600 meters per second downwards, but I already moved 370 kilometers into the surface. Not so likely. So I will, as I did in the code before, look at just showing my simulated path and my simulated velocity. And those are then the observation that comes out. Now I have my own implementation of the Kalman filter, which will work when I do like this. I will not share that code, because then I will also solve assignment 4 for you. So that is sitting underneath. You don't have to implement it as a function as such, you just need to make the loop work right. So I have it as a function where what I have to do is to just give my observations, my A matrix, B matrix, what are the inputs, what are the observation matrix here, what are the different sigmas, my initial state, and then there's a verbose, which is basically just saying I want all the output I can get. So the output that I get is the reconstruction and the predictions, the Kalman gain, the reconstructed sigma xx, likewise sigma yy, and also for the one-step predictions. And if I just take the first element, as in xx, that is reconstructed uncertainty or variance of the position. Take the square root of that, then I get a standard error of the reconstructed position. Then I will plot the reconstructed value plus minus 1.96 times the standard error. And yes, there are actually 3 lines there. So I'm quite confident in being on that red line. The reason is, in this case, my observation noise was much larger than my system noise. So I believe in my system model, and then I only make small corrections. Because what I have up here is that this here, sigma yy, as you also saw in the slides before, sigma yy here is of the order of 10,000, whereas sigma x is of the order, in this case, now it's at 15. So when you take, you can say through the transpose here, but you basically take sigma xx divided by sigma yy. And if this is 1,000 times larger, well, the Kalman gain will be 1 over 1,000, which is small. Therefore, we just use the system. It's just the forecast that really happens. And if you look at the standard deviation of our reconstruction, after a short while, say 10 observations here, it converged to a stationary level. So what I will show now is, even though if I started somewhere totally wrong, the correct position was 10,000 meters above with no velocity. If I now run the same filter, just run the same lines again, plot the data, and then what I predict. What then happens? Well, I said I started exactly just there, 6,000 meters above. Actually, already before plotting, it has been updated because I'm looking at the reconstructed. But I said there was no variance. So, but in just 7 or so observations, I have enough information to actually get close to where I'm at. So even though I started at a totally insane position, it will bring me up. And then after, in this case, 15 observations, I'm sort of back on track, and I can follow the data. So it doesn't matter, we'll discuss more in detail this next week. If you make a small error initially, it's not the end of the day, you just need enough observations. And typically when you have systems like this, you will have updates quite frequently. So that's one of the nice things. So basically, if you look at the standard deviation plot as in this case, it also converges nicely to around 60, whereas the standard deviation of the observation alone was 100. So we reduced, even on the long horizon, we get something that has about half the standard deviation of the observations that we would have otherwise. And if we also plot the velocity for this last case, because we started so far below where we're supposed to be, even started with a negative velocity, what it does is first, it kind of estimates that we're moving upwards, and then backwards, down, and then it's following, you can say, the expected. And of course, you can see if you look at the standard deviation here for the velocity, it's 20 meters per second. It's not too bad. In particular, if your alternative is to just look at observations at some random time, where you have a lot of uncertainty on the particular observations, and just look at the difference in height, then you get a lot more of variance. So this is the same wrong initial state as I just did. And then the last slide is basically just what are the essentials for today. The essential thing is, well, to make the state space formulation, so you can take at least all the linear systems that we looked at and write it as a system equation, first order, and then the dimension is what you increase whenever you have, you can say, more complex systems. Either because you have a second order system initially, which you can give as a two-dimensional first order system, or because you have multiple things that you actually want to track. As in, you want to track both the coordinate, the position in one direction and another direction, maybe even a third direction. You can also do the same thing for rotations. So it's easy to make a complex system. The challenge is, how do we pick the adequate system to a particular case? And then just returning to the fact that almost all systems are observed through sampling. So what you want to do is basically say, well, you sample things, but it's sometimes nice that the underlying model is at first described in continuous time, and then you used different approaches to go from continuous to discrete time. But you can do that. But the system description in continuous time is usually simpler than in discrete time. It's important to just consider if the system you're looking at is actually observable, because if it is not that, there's no point in running through the filter. If you cannot observe the state, you should not go through it. And then I would have loved to have space in here to present the expression for the reconstruction and the prediction, but I have them over here. So that was basically it for today. Now there's one question. But before going to that, I'll just cut here.